we have today to show you a case study of an alternative way of doing cooling and heating with a similar heat pump like any other electric VRV. It's an air-to-water heat pump, and we will show you what possibilities we have with this kind of equipment. The GHP, which means gas-driven heat pump, uses the renewable energy of the air, like any other electric VRV, of course, but then it uses also the primary energy of gas directly where it's needed. So we are missing one conversion from the primary energy to the electricity, which is then used in the electric heat pump. On the other side of the conversion process, we have torque from the engine to drive the scroll compressors, so not different from a car or a truck. And then we have the energy which is released during the combustion, which can be used again for the refrigerant cycle or for the production of domestic hot water. Of course, we have to lose something. We tried to get advantage of what we have on the exhaust gases, but the price for doing that is too expensive compared to the energy we can recover. So as you can see, the refrigerant system of a gas-driven heat pump is very similar to the refrigerant system of an electric VRV. We have scroll compressors. In this case, we have a variable capacity scroll compressor. So there is a third pipe which allows the recycling of some of the refrigerant to keep the efficiency high at very low revolution speed. Matter of fact, those heat pumps can modulate up to the 20% of their capacity. Then we have a usual four-way valve because the cycle can be reverted from cooling to heating. In cooling mode, we use the air to condensate the refrigerant, which is R410A. We have some sensors to monitor the condensation process, and so to change the speed of the fans according to the need of condensing the refrigerant. This allows a reduction of the electricity needed for the heat pump. Then the mixture goes into a supercooling heat exchanger, which is needed because we can reach a very high distance with the indoor units, and we don't want flash evaporation to happen in the pipes. Then, of course, we have indoor units, which can be direct expansion indoor units, so where the freon goes directly for the evaporation. And here we have an electronic expansion valve, which is driven inside the indoor unit by the superheating of the mixture, the evaporator, and then we go back to the outdoor unit and back to the accumulator. So we take the energy from the engine, the mechanical energy, and we use the mechanical energy to drive the heat pump cycle by dragging energy from the indoor unit to the outside in this case. It seems that there is no use for the combustion heat, which is not true because since you have an engine, you also have a second circuit, which is the engine coolant circuit. We use this engine coolant circuit, which is equipped with a double thermostatic valve, to cool down the engine, of course, but also to produce the domestic hot water. Since the combustion needs, the engine needs to be cooled down, at some point during the operation, the coolant temperature is higher than 70 degrees Celsius. So this opens the way to a secondary plate heat exchanger, which is connected to the hot water production on the other side. So basically, instead of using the engine radiator to cool down the engine coolant, we are using a buffer of water to keep the engine down. This also has a positive effect when we are working at very high outside temperatures, because as long as we can keep the engine at the proper temperature, we won't have problems in overheating and damaging the engines. Of course, when the domestic hot water is not needed, what we do is we have another thermostatic valve over there to dissipate the extra heat with the engine radiator. The presence of the domestic hot water kit does not affect the capacity nor the consumption of the heat pump. So this quota of energy that we get is completely for free. we can recover in cooling mode half of the gas consumption. It's a variable speed heat pump, so it depends on how much we are using at the moment. We can always recover half of what we are using. We can use this water for the production of domestic hot water, as I told you before, but in those applications where domestic hot water is not needed, we can also use this quota for the reheat coil of an air handling unit. So it's very useful in case of big buildings where you need also to manage the humidity inside. Or we can work with the simultaneous production of cooling and heating, which is quite a good solution in case of areas where you might need to warm up a part of the building and cool down the other part of the building at the same time. Things change when we start working in heating mode. This is because, of course, we reverse the cycle, but we do not use only the air to evaporate the refrigerant gas. We also use the engine coolant. So, again, we take the mechanical energy from the engine to drive the compressors. The gas goes into the indoor unit where the condensation happens, and so it releases the heat to the indoor of the building. Then it goes back to the outdoor unit, and the most important thing is that on the way back there is no pressure drop, so this expansion valve is always open during the heating mode. The expansion of the refrigerant happens inside the outdoor unit in these other two expansion valves. The first one drives the refrigerant to the air heat exchanger, and the other one drives the refrigerant to the engine coolant heat exchanger. It's a plate heat exchanger, refrigerant on one side, engine coolant on the other side. So you have to think that we have coolant here at 70 degrees almost. So we have a highly superheated mixture here, and we don't care if the whole quota flowing through the coil is fully evaporated, because when they mix together in this point, we will have the proper superheat level to avoid troubles to the compressors. This has a positive effect also on the defrost cycles, because the local temperature of the fins of the coil is not very different from the outside temperature. And so when we are in those critical conditions around 0 degrees where ice starts to stack on the coil of a heat pump, the gas-driven heat pump that is not affected by this problem. You have to think that just behind the coil of the refrigerant gas, we also have the engine radiator, which is warm. So usually when it's a very, very hard working conditions, you can see some stripes of ice on the heat exchanger. You will never see a stack of ice on the heat exchanger of the gas-driven heat pump. So in this case, the recovered heat from the engine and from the exhaust gas is used for the evaporation of the mixture. In fact, when this is happening, we don't have enough temperature to open the thermostatic valve to the domestic hot water kit. So most probably during the winter, there won't be any recovery, or a very small quota can be recovered. So we have to think of something else to produce the domestic hot water when the unit is not working or when the unit is working in heating mode. There is, as I told you, there is a need of peak integration boiler, but it can also be something else. I mean, if we have a cascade heat coming from somewhere else, we can take advantage of this cascade heat. When we speak about the gas-driven heat pump, this is so far, we don't speak about COP, but we speak about GUE, which is the gas utilization efficiency. So when we compare the performances of a gas-driven heat pump with the performances of an electric chiller, we can see that figures don't match. We are used to hear that electric heat pump COP in winter or in summer, ER in that case, is about 4 or higher, depending on the size. Well, you can see from our documents that the gas-driven heat pump has a GUE of maximum 1.6, 1.7. So if you compare 4 with 1.7, there is no comparison. It's better this one because it's 4. But you have to consider that you are working with electricity in the electric heat pump, and you have to convert the electricity to primary energy. So each country has a conversion ratio between electricity and primary energy. What I'm showing here is what we have in Italy so far. So mainly we burn gas to produce our own electricity. Of course we have hydro, of course we have coal, of course we have wind turbines, but on a general average, the conversion ratio is 0.4. So you have available 40% of what you initially burned as a primary energy. When you put this into the heat pump and you use the heat pump, what you have is a gas utilization efficiency of 140. If you do the same with the gas heat pump, there is no conversion between gas and electricity. So you are reducing, you are taking out the production and the distribution losses of the grid. So if you take only into account the refrigerant system, what you have is a gas utilization efficiency of 128. But then we have the heat recovery, which adds 48 extra. In the end, you can reach 176, which means 25% higher performances compared to the electric heat pump. And also you have to consider that the performance stays when the outside temperature drops, because we are using the engine coolant for the evaporation. I told you that we can connect to the direct expansion indoor units, but of course we can also connect with a water chiller or a water unit when the indoor system is driven by water. So our unit is called air-water system, and it's equipped with a plate heat exchanger with an electronic expansion valve. On some versions, a built-in circulation pump for the primary system, and all the safety devices that are needed to prevent the heat exchanger from freezing and the water from entering into the refrigerant cycle. The use of R410 and the structure of the gas-driven heat pump do not allow to have high condensation temperatures. This is why our maximum working temperature in winter is 47 degrees. So it's good for fan coils, it's good for underfloor heating, it's good for air handling unit. It's not good, unfortunately, for radiators, but we can suggest some combination with other technologies to improve the water temperature when needed. We have a variable capacity output also on the air-to-water system, and we can also send the capacity modulation from an outside signal. So there is a program, of course, embedded in the unit, but if we want, we are fully compatible with the building management system, and so we can accept an input signal to modulate the output as much as the user wants. As well as the supply temperature. So actually we can change the supply temperature, and using an external temperature probe, we can also make something like a water changing temperature system. So the water temperature will increase when the outside temperature is dropping. Working with lower supply temperatures, of course, increases the GUE of the gas-driven heat pump. There is a built-in antifreeze protection because the unit can be installed outside as well. So we provided the system with the software to avoid ice to form into the unit, and to reduce the amount of glycol that you have to put in the system to protect it from freezing. The air-water system modulates based on the return temperature. So once the setting point is selected, and once the modulation range is selected, what we can do is to reduce the speed of the engine. So it's not exactly a VRV system when it's air-to-water. It's more like a step-by-step, and we have 4 steps of modulation. So this means that if the building load is 80%, we will work for some time at 100% and for some time at 75%. So to avoid the engine from changing the speed very frequently, we have to foresee a buffer tank for the technical water. This amount of water is, however, reduced, so we can save other money if we compare this system to maybe absorption chillers, which need a large amount of water for the process and also for the cooling tower. Here you can see, for instance, one layout where the buffer is in line with the water loop. This is a 1 GHP, 1 air-water system single, and of course we have a distribution to fan coils and something also coming from low temperature underfloor heating. In this case, you have to make sure that the pressure drop of the circuit does not exceed the available static pressure of the pump, which is built in the system. Otherwise, we can provide an air-water system without pump, and you can select the pump of your choice, which is able to move the water everywhere in the system without losing any pressure. This is the other possibility where we can combine 2 GHPs in one air-water system, and in this case the buffer tank is also the hydraulic separator between the primary and the secondary system. This is what we suggest usually when we have to refurbish a system which is existing, so that you can also make sure that the dirt coming from the indoor system is staying in the buffer tank and is not going into the new heat exchanger. In this case, you have to make sure that the flow rate of the secondary system does never exceed the flow rate of the primary system. And as you can see down here, this is very useful when you have multiple users and you wish to address the consumption of each user and sell the energy directly to the end user. So in this case, we can also calculate how much energy each one is using and address the costs user by user. There is a wide range of GHPs, starting from 22 kilowatts cooling up to 142 in the combination multi-system, which can be connected to a wide range of indoor units or to the air-water systems. So as you can see, we are able and flexible to mix them together and also to make sure that we are matching the need of the building itself. We also have some other solutions like the kits for the air handling unit direct expansion. This is needed for production sites like this, for instance, where you just need a mild air treatment of the premises, and you don't want to invest much money in selecting a very expensive system. This is a modular kit. We can add as many coils as we want. And then we also have, as we saw before, the possibility of monitoring the units from our premises and from the service center premises. This is very important because it allows the service center to see how the system is operating. In the aim of the new regulations for the energy management of the buildings, the monitoring software allows to calculate the delivered energy of the gas-driven heat pump, so you can actually fill in all the requirements for the regulation that foresees that you have to check the unit for leakages, so for the F-gas regulation. Because you can see that the unit is performing, you can see how much energy the unit is delivering at the moment. The case study we are bringing up today is referred to a gas station in Italy. This unit is 20 horsepower, so it means 50 kilowatts cooling, 60 kilowatts heating, and it's air to water. The cooling heating is for the restaurant and for the shop of the gas station, and also for the production of domestic hot water, because there is a truck stop on the other side, and they have showers and they have facilities for truck drivers. So what I'm showing you is a running cost comparison. This is, of course, based on the price this customer is paying for the operation of the system, and it's based with the old system which was here, which was made with a gas boiler and an electric chiller. So in winter, we made a comparison based on 187 days heating mode, something like 2,800 running hours. So the system with gas boiler needed 18,419 cubic meters for the whole reference period, which meant almost 100 cubic meters per day in the consumption. The year after, when the GHP was installed, we had a gas consumption of 12,248 cubic meters, which means 65.5 cubic meters per day. Of course, we also wanted to compare what was going on in summer, because we sold the unit to the customer, saying that he could spare the electrical cost of the chiller throughout the winter, because of course if you have a 50 kilowatt, 100 kilowatt chiller, I mean electrical consumption, you have to pay the amount the whole year, even though you use the chiller only 3 months maybe. So in this case we made a comparison based on 120 days of cooling mode, almost 1,000 hours. The electric chiller needed 18,795 kilowatt hours with a daily consumption of 156.6 kilowatt hours. But then we also had to calculate how much energy was needed for the production of domestic hot water. So the gas boiler went on with 1,295 cubic meters, which is 10 cubic meters per day only for the showers. All in all, the GHP produced in the 120 days the same amount of domestic hot water by cooling the restaurant and the gas station and using only 4,444 cubic meters of gas, which is about 37 cubic meters per day. So let's compare the figures. We had a gas consumption saving from one year to the next one in 3,137 cubic meters of gas, which means something around 1,800 euros. And we also had 16,275 kilowatt hours electricity that we didn't use. So something about 3,255 euros. All in all, the running cost saving of the gas station was almost 5,000 euros, which is about 39% compared to the year before. And also, we had the possibility of reducing the electrical contract of the gas station for the heat pump quota, for the water chiller quota, 19 kilowatts of capacity, and an annual saving of CO2, which is comparable with 15 tons. If we go back to the primary energy annual saving, what we were able to save in 1 year with the operation of the gas-driven heat pump is about 78,506 kilowatt hour of primary energy. So as you can see, we have other gas stations in Italy. Some of them were made in 2001, some of them were made in 2006. This one I'm showing was refurbished in 2012. So many applications like this. So the GHP can be flexible for new installations, for refurbishment of old installations, if you need direct expansion or if you need air water system, and if you need domestic hot water. The GHP is eco-friendly. There is a rational use of primary energy, and there are reduced consumption, and there is also reduced CO2 emission. So the carbon footprint of the GHP is reduced. The GHP is efficient because it has a reduced payback time, low running costs. This unit runs on Toyota engines, so those engines are quite reliable, and long maintenance intervals. You have to think that the manufacturer says the engine lasts 40,000 running hours. Our experience, we have some units which have reached more than 75,000 hours with no issues on the engines. So we know for sure that the engines are well designed and reliable. In the end, what I would like to say is if we can use more GHPs, we need less power plants, which is what we are aiming for, because we are talking about reducing the carbon footprint, we are talking about reducing the global warming of the Earth, and so go to new refrigerants to reduce the impact of the refrigerant gases on the CO2 emissions, but also the use of new intelligent technologies can lead to energy saving. Thank you very much for your attention. I'm here if you need anything, if you have some questions.